Okay, so today's lecture is about free monads, which is a second way to more or less easily generate new monads. So last lecture was about monad transformers. It's like the standard way to basically assemble custom monads that have custom effects, and free monads is a different way with different goals as well. But before we come to free monads, the first half of the lecture is basically just a case study of monad transformers. And then we will use that to then second half of the lecture talk about free monads. So let's start with this case study. And before we do, let me just rename something quickly. Okay. One second. I just want to keep the two halves separate. Just see whether that works. Okay, fine. So we start with this very simple type of expressions. So we just have two constructors, integer literals, and we can add two expressions. So let's start with that. And do a oh, doesn't matter. Just for debugging, sometimes good. Okay, and let me also open REPL. Okay, and I mean, now we could do stuff like add whatever, lit1, add lit2, lit3. But when I say do stuff, I mean, we can define this, but of course it doesn't do anything yet. So we obviously would like to evaluate. So let's write an evaluate function, which takes an expression and evaluates it to an int. And of course, I mean, that's just standard design pattern on functions. So the expression type has two constructors, so we give two equations. And if we have a literal, integer literal, it just evaluates to the appropriate literal. And if we have an add, then we just recursively eval the two parts and add them. We'll reload and then apply eval to the example expression I had earlier, I get 6. Okay, so far so good, and that's basically week 1 Haskell. Now let's say we want to extend this expression type. We want to also add division. And let me just keep the old version for later reference. So now, first of all, we must also take care of this division constructor. And secondly, now something can go wrong. I mean, we can have division by 0. So we also change the return type, and let's say we change it to either string int. So a left means there's an error with a string error message, and the right means there was no error and we get a result. So now, because I'm in either, earlier I had return type int, so now I have either. So I can do write n, or I can also use the fact that either string is a monad, so I can use pure. Same here. Let me just check what I did in the slides. Right. So if I want to stay in this monad, then I can use applicative syntax. I can do well x y, and now of course I have to add a case for this constructor. And so there are two cases. If y is 0, then I do a error. What is it called? I just want to, okay, division by 0. Otherwise, it's pure. Oh, sorry. It's div x equal y. So throw error is not in scope. I can import this. Oh, that's sorry, that's decrypted. That's an accept. Okay, and in, this is from the MTL library that we introduced last time, monad transformer library. So there we have this class monad error for monads that can throw exceptions of type E, and either is an instance. Therefore, we have this throw error. Why do I get an error there? Oh, sorry. Yes, that was wrong. Sorry. I first have to, this y is not an integer, it's an expression. So I have to first evaluate that. And now I can well, I can do it in monadic style. For example, like this. Let's try it out. So if I have like what I had before, of course, I still get 6, except now it's write 6. And if I use, I don't know, now this div, for example, 12 divided by 3, and I get 5, because 1 plus 12 over 3 is 5. And if I divide by 0, I indeed get an error. So that's good. So it works. However, in order to get from the first version I had to the second version, I basically had to completely rewrite my code here. Every single line I had to touch. And of course, because here I had a pure, just a pure function. And here I switched to like a monadic result type, where the monad in this case was either string, and then of course everything, also literal and addition had to change, even though in principle the only new thing was division. So just check, sorry. Right. So let me just go back for a second. So take this case out again, and now comment that one just for a second. So if instead I hadn't started with this type for eval, but instead of int had used identity int, so the identity monad, which I must import. Now it's from control monad identity. I could also import it from, I think in previous lectures, I imported it from data or control functor or data functor identity. Doesn't matter, it's the same thing. Right. Then this is pure n, and this is indeed like this. And just try the original example again, the one without division. Okay, and now the point is, if I now revert this again, and this, if we now compare the two versions, they are much more similar. So, I mean, of course, this one is a bit more complicated than what I had before, because now I have this identity new type constructor and need to use pure and this applicative style instead of just writing eval x plus eval y. But on the plus side, if we now compare these two versions, these two lines here, 14 and 15, haven't changed at all. They're completely identical. So what has changed is I have used another monad. I started with identity. Now I have either string. And of course, I needed a new case for the diff case because now I have this new constructor here. But the point is it's much more, I mean, I don't have to fundamentally change everything by adding this one new constructor. I basically just can take what I have, make minor adjustments, and then mostly concentrate on adding this new case. Right, let me just check. So here we had this, and we make the observation that affects every line. We have to change everything. But if we switch in the simple version to also using a monad identity, then only this new row is added. So it's basically a trade-off. We have to accept that we are now using applicative or monadic style for our code. But the plus side is that when we try to extend it, it only has a minimal effect on the existing cases. And the plan now is to somehow abstract that a bit away. So we will define a monad eval and will slowly add features. And we will implement those features using MTL, the monad transformers. And we will try to do this in a way that when we add features, we don't have to change much of existing code. And maybe I should, right, maybe I should actually put a new model for that, or create a new model, I mean. Call it eval. Just do this quickly. Let me update this here. Oh, I did that already. I must just close this. Don't doing optics anymore. Okay, MTL. Okay, just check whether it still compiles. Right. I mean, I don't need identity anymore now. Can remove that again. Okay. And right, the idea is now to basically not use this monad directly, in this case, either string, but somehow abstract it away. So use some other type for it. So let's do this for a second. Right. So let me do this here. So data eval a. And for the time being, I just I just give a dummy implementation basically. So we have let's diff by 0 error. Okay, diff by 0 error is eval a for any a. And I don't implement it yet, and the other one is run eval, and it gets an expression. Sorry, gets an eval. Runs either string a. And I mean, at the moment it's anyway dummy implementation, but I just export the type, not the constructor for now. And these two functions, nothing else. Okay, I mean, this is now like this, and now I can import this here. And now I can instead go to eval int. Okay, and this is now just diff by 0 error. Right. And this now doesn't work because I don't have an explicit applicative or monad instance. So what I also need here is instance functor eval where instance applicative eval where instance monad eval where. Okay. And I can do fmap is lift m always. Pure is undefined for the time being. Return is pure. And bind is undefined. And I need the up. And then must import those things. Right. Okay, now I think it should compile again. Okay. So, I mean, now I made it even more complicated, but the point is that I now separated the interface of this eval thing from the implementation. And now I can write this code basically without caring what concrete implementation I'm actually using. I mean, of course, at the moment, I don't have any implementation. Now I could, of course, do this again. So let's now implement that. So for the time being, can just do new type eval a is eval. Let me just see what I do in the slides. Right. So I can use except t string. So at the moment, the only special thing I need is error messages of type string, and use the identity monad. So now there they come again. T. Okay. And actually, now I don't need all of this because I can automatically derive everything. And now this is a new feature that we haven't seen yet. So that's also very useful. I mean, we know that we can derive functor automatically. if we activate this extension derive functor. This is now a new, but we can't automatically derive applicative and monad. However, what I wrote here, this except T monad transformer, that is called a monad transformer because it transforms monads into monads. So identity is a monad. So except T will also be a monad. So we know that this here is a monad. And now we're just using a new type wrapper around it. And intuitively, because a new type doesn't change the runtime presentation, it's just basically a new name for an existing type. If what I wrap is a monad or any other type class, then wrapping it in a new type should also give me an instance of the type class. And there's an extension for that, which implements just this idea. It's called generalized U-type deriving. So I don't need this here anymore. So that allows to derive instances of type classes for new types if the thing that you wrap in your new type has the instance. So because except T string identity is functor, applicative, and monad, by using this extension, I automatically also get it for this new type for eval. Right now, I, of course, have to implement this. And actually, I can, because I know except T is a monad error string, so I can add this as well. Sorry, monad error string. Must import that, of course. And actually, I need the methods. And now I can implement this simply as throw error division by 0. Right, let me just check whether everything still works. Yep, and now finally this run eval. We had that before. So if I have an eval m, then just run except tm. I think that should, sorry, wrong button. Yeah, can. Okay, and now it gets so what does run except t do? Okay. So I mean, except, so run except t takes an except t EMA, like my m here, and produces m of either EA. And m in our case is identity. So I still need a run identity. Or is it get identity? I think it's run identity, which I must also import. Okay. Right, so now I've implemented everything. And now hopefully we just restart this. RTL. Right, and now the old examples should work again if I still have them. No, I don't. So I can do, for example, run eval. Eval, was it at that one at the 2, 3. Okay, so it's as before. And if I use diff instead, also works. And if I have division by 0, I get that. So I have the old old behavior back. But the difference is now I have like split the actual implementation of the monad away, or separate, abstracted it away. So in order to write this eval, I only need to know that eval is a monad, and I have this special operation division by 0 error basically. And just using that, I can write this code, how to evaluate an expression. And then the actual implementation of this monad, of the interface of the API, so that I have diff by zero error and run eval in order to actually run it in the end, I have delegated to this module here. So at the moment, not much has happened. But now it's like arranged in a way that it's easy to add features. Please feel free to interrupt me if you have questions. Right, so I explained in particular this generalized new type deriving. That's a very useful extension. So, and especially for these monad transformers, that is often used because the MTL library has all the instances. And then by using generalized new type deriving, one automatically gets them for new types as well. So I did this. So now we want to extend our thing again with variables. Before I do that, before I give you variables, I just also need containers. Okay, so I want an additional constructor, namely variables with a name. For simplicity, just the name is just a string. And let me just see how it's done here. So of course now I need, and the idea is that in the end I will, in order to run it, what is supposed to be the interpretation of these, or how is eval supposed to work for variables, so that I have an environment where variable names are mapped to integers. So that means I want to change the type of my run function. So it doesn't just take an eval A, it in addition takes an environment. And an environment I just define as, I think we have had that before, map string int. I must import data.map map. Okay. And I must somehow have something to actually look up something in the environment. So I can call it lookup. What is it called here? Var lookup. Okay. So I want something var lookup. Names. So given the name of a variable, want to be able to look it up. This, of course, now doesn't, well, it does compile, but right, I haven't defined the var lookup. Okay, but this compiles at the moment. So now I can easily do the additional case. So I can leave all of this untouched and I can just say eval var s or var n for, yeah, s is var lookup s. So it's very easy, and I don't have to touch any existing code. I just have to add a new case here for this new constructor. So now, of course, here I do have to do something. So now we have variables that we can look up, but we can't change them. So that screams like reader. So in order to implement these things, I can add an additional layer here to my monads, so I can add a reader T env layer. Of course, I must import this. Okay. Reader T. Now I also can derive monad reader env. Eval. Of course, must import monad reader as well. Sorry, monad reader env, not eval. Same as monad error string. Okay, so now I can implement this var lookup. So I can, so S. So now, because now I have a reader monad, I can ask for the environment. And then I can look up whether the key is in this environment. Okay, so case map lookup the name of the variable in the environment. And if I do find it, then I just return the value. And if not, so I can do another exception. So I can actually factor this out. Let me just check what it's called here. Yeah, unknown variable. Variable s throw error unknown variable s, and I can use this here. Okay, and the last thing I need to fix is this run, because now I don't have I mean, I changed my monad, so this won't work anymore. So now I have, I mean, first of all, I need a run reader. M. Oh, sorry. Yeah, it's true. I mean, first I must do a run reader M with the given value of the read-only state. And then I'm in the situation that I was in before. So then I can do the run accept and the run identity. Okay. Right. So let's try it out. I must restart the REPL because I added containers as a dependency afterwards. Okay, so now I can do run eval, whatever. Let's start as before. Eval add lit one, add lit two, lit three. Now I must give this environment. Right, and that is not in scope. Okay, now. So for example, I can just use the empty environment because at the moment I'm not using variables. So that works as before. We can also check the division and the division by 0, whether that still works as before. So I'm not making use of variables yet. Okay, this works. And also try division by 0, whether that still gives an error. It does. And now, of course, we want to make use of variables. So instead of dividing by specific integer, let's divide by variable x. Right, so if it's, so right now the environment is empty, so x is not defined, and I do get an error, unknown variable x. But if I now put x into the environment and, for example, set it to 3, then I get 5 again, like in this example. So that works. And note that what we had to change, so in order to extend this, I added this one new constructor. I didn't have to touch any of this code. I only added this one line. And then in the actual implementation, okay, so I extended the API to also do this var lookup. I changed my monad. I added the reader T transformer so that now I have access to the environment. I didn't have to touch this. I didn't have to touch the, okay, I didn't have to touch this. I added this and of course the variable lookup. I mean, that's the new feature. So this I had to add, and the runner, I had to slightly modify it. So it now takes an additional argument, this environment. And I mean, earlier I just had run identity run except T, but now I first have to unwrap this reader transformer. So I had to change something here. But basically only stuff that was directly related to the new feature. So as a final extension to our little expression language, let's add 2 more constructors. So I also want to set variables, and I want to have like, let me just check here. Change so this works. Right. So I want to add 2 new constructors. So sequence is basically like a semicolon, so that we can have several statements like in a program with several lines or several commands, and assign a value to a variable. So let's do this. So seek expression, and assign string expression. Okay. So actually I only, okay, this assign we don't know, but seek we can already handle just like this. So if we have seek xy, maybe just eval x, and I mean, we know it's a monad, so we ignore the result and then do eval y. So that should compile. We should just get a warning that we haven't done assign yet. Okay, and for assign, we can just add a new primitive. So let me just check what it's called. Okay, var set. So given the name of a variable and the value, right, we set it. And given this new primitive, we can also here now implement this assign. Just try to align this a bit. Okay. So how would that work? I mean, making use of this primitive, we first must evaluate the x to an integer. So we can recursively call eval on x. Then we can use this set, what was it called? Var set, sorry. Var set So the name is S, the value is N. And now we want to, we are supposed to return integer, so we can do the N. Okay. Right. So again, here I didn't need to change anything for the existing cases. I implemented the sequencing and I implemented the assign. And I need one more primitive in my eval monad to actually do this, or one new API function. So now, of course, we need to implement this here. And how would we do that? Now, because of this assign, we want to be able to change the environment. So the obvious idea is to replace reader T, which is for read-only state, by state T, which is for mutable state. Because I must import this and just see, okay. State T, and I also want monad state. And now I have, instead of monad reader, I have monad state. And now here in this var lookup, ask I don't have ask anymore. In the state monad or monad state, it's called get. But everything else is the same. And of course here, instead of run reader T, I now have run state T. And now there is one additional problem. Just a second. Sorry, I haven't saved yet. Right. Remember, state returns a pair, a tuple consisting of the value and the new state. In this case, I don't even care about the new state. So instead, I can use eval state, which has the right. Let me just see, must import this. So now this should now compile again. Right. And I don't need the monad reader stuff anymore. Right, so it compiles again. Just as a reminder, so if I import control monad state, then the type of run state T, so it takes a monadic computation and an initial state, and it in M returns a tuple consisting of the result and the new state. And there are these variants, eval state, which ignores the new state. And there's also one that we don't need now, but just for completeness sake, which does the opposite. So it ignores the result and just returns the updated state. In this case, if we use eval state, then basically we don't have to change anything about our runner, except that we replace run reader T with eval state T. Everything else is still fine. So all we have to do is implement this var set now. So name value, and we can just use modify. So if you recall, okay, fine. We just do undefined. So modify updates the state in a monad state, in the state monad. So given a function from old state to new state, it just does that. So in our case, what do we want to do? The state is this map. So we want to set the value for key S to value N. So we just do map insert Sn. Right. So here I had to change very little. I added this var set. I modified the monad. So instead of reader T, I'm using state T. Now I have monad state instead of monad reader. This could all stay as it was. The runner had to be slightly modified by swapping out run reader T for eval state T. And of course, I had to add this new functionality to set a variable. And on this side, I, of course, had to add the 2 new clauses for our 2 new constructors. But everything else could stay exactly the same. Now, of course, we want to see whether it actually works. So let's start simple again. That's still, yeah, it's still in scope. So this still works. Actually, I mean, that's not on the slides, but I could do it simpler now even. I think the way I would do is I wouldn't even bother about an initial state because now we have this sequencing. So we can just start with the empty state in the beginning. I mean, this, I think in the slide it's differently, but I think this is actually nicer. So now in order to so we don't need this argument here anymore. We can get rid of some questions. Now, of course, X is unknown, but now I have this sequencing operator, so I can do assign X3 sequenced with this lit3, sorry. Okay. So yeah, and also try that the other stuff still works. So for example, assign it to 0, then I get a division by 0 error. Okay, and of course we could now add more features if we wanted. I mean, we wanted a real, I mean, this is now a toy programming language, so we can, because of the seq, we can already have like several statements sequenced. We can, because of var, we can access variables, we can assign variables, and we have addition and, I mean, we have integer literals, we have addition and division. Obviously, it's still very primitive. I mean, we could add multiplication and other arithmetic operators, and then of course we would also want to do branching or loops or whatever. But the point, I mean, of this exercise or this example is not to implement a programming language, although, I mean, one of the things Haskell is really, really good at is like writing compilers and interpreters for other programming languages. So if you ever are in a situation where you would like to implement a programming language, then Haskell is very well suited for that. But anyway, the main point of this was to show how basically programs evolve, also like real world programs in Haskell. So, I mean, often it involves a monad that you work in. I mean, maybe, I mean, there can be a global one for the whole application, or maybe we are just talking about certain parts of the application. And this design pattern that you basically have the monad more or less abstract. So maybe wrapped in a new type and the constructor isn't even exported, just some type classes. So you know it's a monad, for example. And then maybe some specific functions working with this monad. And then you implement your actual business logic against this monad. And by doing it like that, I hope that example shows this by, I mean, it makes it normally very easy to add features. So once you realize that your monad is no longer powerful enough or that you need extra effects, you can easily like change the implementation without having to change too much of your business logic. So normally then it's minor changes. The existing code can stay intact and you only have to add logic for like new cases. So I think that's, I mean, that's quite an important technique that's often used. And it shows how, I mean, also how MTL is used. I mean, whenever you realize you need a new feature, it's easy normally to take one of the standard monad transformers like state T or except T to add the feature accordingly. So are there any questions at this point?
I don't think no questions so far.
Okay.
No. No.
Let me just check the slides whether I forgot anything. So, okay, as I said here, the run function still takes the initial environment. I just think it's more natural in this case because normally if you have a program in some programming language, in the beginning, no variables are assigned. So you start with the empty environment and then over the course of your program, you extend the environment. So yeah, whatever. Okay, here's an example. Right, and we can do that as well, I suppose. So what does it do? It says X, let's just try to type it just as an example. So we assign 16, is it? Then we assign X to X divided by 2. And then we add 1. Because I can try this as well. Run eval program. We get 9, right? I mean, this is like in some imperative language. Why? Yeah. Basically like this. Right, and we get 9 as expected. Okay, so basically the summary up to this point is that by using this abstract monad, so abstract in the sense that we didn't export the implementation or even the constructors of eval. So we only had the fact that it was a monad with these additional functions like division by 0 error. And that allows us to extend code with new kinds of effects without affecting much of our existing code. Then we saw how easy it is using these monad transformers to add the features we need. So we basically did that 3 times. I mean, we started with identity, no features. Then we added these exceptions with string error messages by using except t. Then we wanted read-only state to be able to look up variables. So we added a reader t layer. And then we changed our mind and said we should also be able to assign variables. So we use state t. But picking just suitable monad transformers made it very easy to implement these monads with the features we wanted. We didn't have to write a single instance of a type class by hand. And of course, just as a reiteration that there is this catchphrase that monads are like a programmable semicolon, to which each step, the bind, of course, changes because we changed the monad. So, but the program still looks the same. I mean, this basically, but what the bind now does, I mean, now because we changed to state t, so now the current state, the current environment is threaded to these operations and so on. And before we had state t or even reader t there was no threading through of state, but we always had like an either result. And if we get a left, then we immediately stop. So all these different behaviors coming from the different transformer layers, I mean, we can easily swap and combine. So that's that.
Yes, Jason said that this make the use case for modal transformation much more clear.
Ah,
This case, yeah.
nice. That's good. I'm glad to hear that.
Yeah.
Okay, I just want to check quickly. Right. So I think, I mean, we are only at it for like a bit less than an hour, but this would now be a very natural spot for a break. So I suggest we may have our break now, maybe a little bit early. And then we basically come to 3 monads after the break. So maybe a break until 3:15. Sorry, not 3 your time, but 3:15. And
Yeah.
then, okay. Okay, I'm back. Should we continue?
Okay.
Okay. Before we do it, let me just briefly, what did I have now? I had MTL. Right. But let me just change that a bit. Sorry. I just rename stuff a bit. So I actually move what I called MTL. I call that expression. I let me just clean that up. So now I have MTL and expression. Let's just rename stuff. This is now MTL. This expression. Sorry. And it imports MTL. Actually, I don't have to import anything here. Right, but this, let me just move that other one. I import expression here. Right. And right. See. Okay. I'm safe. Okay, so I just separated basically everything that's specific to this MTL stuff into the MTL module, and just the expression that doesn't mention any monad or anything. I just moved into this expression module. And now let's add a new one. This 1.3. Add that here. Okay, so that's now free. Oh yeah, I don't know, this I could have moved maybe to here. Second. Okay. Right. I think now. Oh, come on. Don't need that anymore. Yeah. Yes, Karina?
No, I just say that they need to rewrite some and save.
Right. Okay. So everything compiles again. I just moved it a bit around. Okay. So now the idea is, I mean, the idea was we had this implementation module, and then we exported like it without constructor and so on, and we had these special operations, and we could write an evaluator. So now but I mean, we needed to give a concrete implementation that we did with monad transformers. And often there are situations where maybe you have different possible interpretations or implementations of these things. I'm not sure whether this now is a very good example for that. But for example, I gave you this Monty Hall example with the monad randoms thing. They had this special operation of what was it, throwing a die or flipping a coin with a certain probability of heads. And there I basically gave you like different implementations, like one can do it in IO, and I also gave you this idea how one can do it like explicitly with a full probability distribution. So often there are situations where there are several interpretations for certain operations. Typically also for testing. Sometimes you want to, like in production, run something in IO with real world side effects. But for testing, you want a pure implementation where you can mock all the side effects and just have pure functions, and that are much easier to test, for example, with quick check. Incidentally, IO or IOG uses that for our node, for example. So we have something called IO sim, which is like a version of IO that has two interpretations, real IO and also pure interpretation. And we use that to like write unit or quick check tests for our node code. So we have this IO sim monad that, depending on how you configure it, can act like real IO monad or also like a pure version where everything is deterministic. So that's often useful. So the idea is it would be nice if we like had an actual type eval that doesn't already basically force us to a specific implementation. So what do we have? We have diff by 0, running var lookup and var set, and I think here is right there these things. Right. So I mean, our pieces where we had this data type, the expressions, then we wrote the evaluator against the abstract monad, basically this eval monad, which we sort of wrote down like this, and we implemented this using monad transformers. And now the idea is, or the question is, can we basically define a type eval that is just abstract? It allows us to write this interpreter, but it doesn't already tie it to an implementation. So basically an abstract version of the eval monad that is already a monad with all these operations, but it's not yet implemented as a concrete monad transformer stack. And as I said, so in principle, the idea is to like reify the interface, make the interface a concrete type. And then it's possible to write programs using that concrete type, but then have different implementations for the interface. And basically have these programs, these abstract expressions in the abstract monad available as data that you can then analyze and maybe transform or compile or whatever. And the basic idea is to turn functions into constructors. So basically we try with something like this. So let me start with that. Sorry, free now. So we define an eval. So we have this, let me just get the names right, diff by 0 error. So just to check, so the idea is, I'm sorry, here, to take all these things that were functions and now make them constructors of this data type we are working at. So this is diff by 0 error. Then I have this unknown variable, known var, which takes a string, the name of the unknown variable. Then what else do we have? We have the var lookup and the var set. Var lookup, which takes the name of a variable, and var set, which takes the name of a variable and the new value of the variable. Okay, so that's like the idea. So we take these special functions we needed in order to implement our interpreter, and turn them into constructors of this type we are building. Okay, so I mean, this is, I think it would compile. Okay, so far so good. But we lose information when we do this. I mean, we had, if we look here at MTL, for example, var lookup, that gave us an eval int. Unknown var and diff by 0 work for arbitrary Rs. Var set gave us a unit. So we somehow lose that information. And it's also not clear how we want to actually implement monad for this. So, I mean, we want to write something like instance functor eval. Instance applicative eval. Monad eval. Right. And the first problem, let me just want to write. Right, so the first problem is these return types. So we would like to give this diff by 0 error and the unknown var string, those two constructors, they should have like return type polymorphic A. The var lookup should have return type int, and the var set should have return type unit. So that is something that we can't do. I mean, if we have this data constructor, or at least not easily. So, I mean, the data keyword we basically learned in our very first Haskell lesson. And we also know many examples where it takes type parameters like this A here. But when we do it like this, the return type of these constructors is always eval A. So it's always the same. So it's always for the same A. So just, I mean, this will now, right, I mean, it gives warnings, of course. But if I ask for example, the type of var lookup, can't I? Right. So it gives me an eval A, and this is just how the data keyword works. If I define a polymorphic type, then all the constructors give me a value of that type. So if I have type of var set, also eval A. But that's somehow wrong. I mean, I want that the lookup doesn't give me an arbitrary eval. It's supposed to give me an eval int. And the set should give me an eval unit. And I mean, there's no way to do this. This is where quite important and relatively recent extension of GHD comes in, so-called GADTs, generalized algebraic data types. And before we continue here, so let me just, so it's called GADTs. Right, before we continue there, let me just do, for example, our trees. I mean, we had one example was always our tree A type, and we had leaf A and node tree of A, tree of A. I mean, this was one of our standard examples. Another example, for example, lists. I mean, they are built in, of course, but if we wanted to define our own version of lists, would have one constructor for the empty list and one constructor for a non-empty list. Okay, and now what this extension allows us to do is to rewrite such data declarations or definitions of no data types in a different syntax, so-called GADT syntax. And first of all, I mean, first, it doesn't change the meaning. It's just a different syntax. So if I wanted to write these in GADT syntax, what I do is instead of the equal sign, I have a where. And now for each constructor, instead of just listing the constructor name and its arguments, I give the what's the word? Sorry, signature. So let me just do it back. So, and let me just make this a little bit bigger. And let's just ask, I mean, for the type of leaf, the type of node, the type of nil, the type of cons. Okay, and so first of all, what GADT syntax allows me to do is I replace the equal sign with where, and now each constructor with its signature. So instead of writing leaf A, I basically write exactly what I got here. So I now write leaf as signature A to tree A. On node, also no vertical bar as signature tree A to tree A to tree A. Same for lists. So nil has signature list A, and cons takes an A and a list and gives me a list. And okay, fine. And that doesn't change anything. It's just a syntactic change. So if I ask for the same types again, I get exactly the same answer. So I haven't done anything new yet. It's just a different way of writing data types down. And I personally like this. I mean, of course, it's a matter of taste, but I mean, you could always do this. So instead of writing it the way we used to do it, you could always use this GADT syntax. You must just activate it. I like it because somehow, I mean, it gives you the signature. So it's a bit more explicit than the normal way of writing data definitions. But again, nothing new has happened yet. So we can, of course, also do that for this type here. So just okay, so again, I haven't changed anything. I've just used the syntax. And incidentally, I think there's also an extension that I never use, but I think it's called GADT syntax. So this allows you to do exactly what I've done now. So you don't have any extra power or anything like that. You can just write data declarations in this form, in this so-called GADT syntax. Right, so far so good, and we haven't done anything new. But now the interesting point of GADTs is that in these syntaxes here, you don't have to write eval A or tree A or list A. You do have to write eval or tree or list. So it must be the type you're defining. we're defining eval. So all these signatures must result in an eval. We're defining trees, all the signatures must give you a tree. We're defining lists, all these signatures must give you a list. But the A, you are now free to put something else there. So in our case, we want that the var lookup gives us an int and that the setting of a variable gives us a unit. And that I can now do. This is what is new, what is not possible with non-GADT. So that's where the G comes in, generalized algebraic data types. So this is, I think it's a very nice extension and it's extremely useful. Can do very nice things with that. And I think it's relatively easy to understand. I mean, of course, it's always a matter of personal taste, but I think in comparison to optics or monads or so, it's a very easy to understand extension, but it allows you to do very cool things. Maybe we will see some of that, but right. So this is what GADTs allow us to do. So now we have basically fixed the first problem, that we now do have the result type again. So now we know that. So if I save that and now ask for the type of, for example, var lookup, it indeed shows me it takes a string and doesn't give an eval for like a polymorphic eval, but specifically an eval int. And var set specifically gives me an eval unit. So this is now possible because of the G in GADT, generalized algebraic data type. Right. And I mean, to get back on track, I mean, what we want to do is we want to be able to write this evaluator basically. Right. And let me just copy this and put it here. Okay, fine. Just, I mean, this was not an example. That again, or I can also see if it commented. Okay, now we don't have these functions anymore. They are now constructors. And just to reiterate, before I use the GADT, so if I had like before an A here, for example, and here, then this and in particular this would like warn me. And of course it's, I mean, because this is now like I am discarding a result, and this is also, I mean, it works because I specialize it here for int, but I mean, it's just not correct because I can't get an arbitrary value out of it. I mean, I can only get an int out of it. So, okay. Now, of course, the problem is that these things, I mean, how am I supposed to write functor, applicative, or monad for this type? How do I return and how do I do bind? And right. Okay. I mean, the first part is boilerplate like always. So I can do fmap is lift m. Do this. I can do app is app. And return is pure. That I don't know, and pure I don't know. Okay. And the idea now, I mean, the first idea that we will refine a bit later is to basically cheat. I mean, we are defining this abstract type. Everything is abstract anyway. I mean, we can't really compute anything. Is to basically just add what's missing. So I just add pure with the right signature. So A to eval A, and bind also with the right signature. So eval A to eval B, eval B. I mean, I'm free to pick whatever constructors I want, right? So I just pick the right ones, and then I can just define pure as pure. And bind as bind. Okay, so far so good. Now, of course, so that will compile, I suppose. But of course, I can't compute anything. In particular, I can't, let me just check right here. I mean, I don't, I mean, I can't like concretely evaluate anything. But so now the idea is to somehow write an interpretation of this eval type, of this abstract eval type in terms of my MTL code that we did earlier. Let me just check for, yeah, okay. Okay. I see on the slides it's slightly different. So on the slides, sorry, wrong model, this one. The slides, I left it like this. Like before. And now I have this helper functions. So can do that here, for example. So diff by 0 error A. This looks a bit silly now, but it will become more interesting later. I basically just recover my functions from before by just defining them as the corresponding constructors. That was wrong. The import was wrong. That happened automatically. I remove that now. That was that. Okay. Why is now everything? Yeah, okay, because I don't need this. Right. Okay. So now I have like literally exactly the same code as before here. Except now it's not the MTL using eval monad, it's this one. And now the idea is to bridge from the one to the other by writing an interpreter. So something and for that I import qualified the code I had before. So free monads MTL as MTL. And now I write an interpreter from eval, which takes my abstract eval and converts it to a concrete eval. Okay. And this is now again just a simple function. So I must just have an equation for all these constructors. So diff by zero error, for example, you can just use MTL, diff by zero error. Why? What did it now import? I don't know. Weird. Because it didn't import anything, did it? Right, let's
No.
okay, what's
No.
maybe I should I'm just wondering whether I should write it. Yeah, this way I always have to scroll. Let me write it directly here and make this a bit smaller. Okay. Okay, so I mean it's relatively boring. So unknown var s is MTL. I didn't I export that? No, I did not. Let's rectify this. Okay. Unknown var s from eval var lookup s MTL var lookup s from eval var set s n MTL var set sn. Okay, I suppose I have to export it if I want to get rid of the warnings. What next? Pure and bind. Okay, right, of course. So from eval pure a, it's just pure a, because I know MTM eval is a monad, so I have pure and bind. And from eval bind m and the continuation, it's just m and the continuation. Oh yeah, sorry. And now I must be careful because this is now of the wrong types. I mean, this is not of MTL type, so I must recursively do from eval m. And now the continuation goes from A to eval B. But of course, the MTL, I mean, which is also the wrong type. I need something of type MTL eval B. So I must compose this function, the continuation, with from eval. So I have okay, and now this compiles. Whatever. And now it should, I mean, I should be able to test it. So now I can do run eval. Sorry. Let me do this. Let's do it here. So I can do test is either string int. So I can take my example program, evaluate it, and note that that eval is this eval, which uses this abstract eval type. So it doesn't have anything to do with MTL. So I get something of type eval int. Now I can use my interpreter to interpret it in MTL. So I can do from eval. And now I can use the runner that we defined earlier. So MTL run eval. I can try it, and I get the correct result. Okay, right. So far, so good. So that looks promising. So we have this abstract type, this abstract eval type, which has constructors for all the special operations we need in this monad. But it's just, I mean, constructors. It's just datum what we construct here. It has no behavior. It doesn't do anything. And I added this pure and bind just to be able to implement monad for it. So which feels a bit like cheating. Then I defined these helper functions here, which are just other names for the constructors at the moment, just with lowercase instead of uppercase. And then I could use the exact same interpreter we wrote earlier for a specific monad, constructed using monad transformers. Now, instead, going to this abstract monad here. And exactly the same interpreter. And given an interpretation, this from eval, I could actually try it out. So now, of course, the idea would be if I had another interpretation from eval prime, I could use the same evaluator here and basically interpret it in another monad. So that's the idea, and it seems to work, and that's so far so good. I mean, it's already quite nice, actually. Are there any questions at this point?
I think no questions so far. Yeah.
Good.
They are very
Right.
interested in the explanation. Yeah.
Okay, good. Right, so now let's go back to the slides. Did I do anything wrong? I think not. Right. Right, now let's recall the monad laws. Because we said earlier, I mean, it's not enough to somehow implement like pure and bind. They are also supposed to follow these laws. And I mean, of course, that's always a bit vague in Haskell because the compiler can't enforce it. And I said, normally, if you implement a monad, then you are supposed to check that the laws hold, or at least, I mean, if you publish a library, for example, with a monad, then people would normally expect that it follows the monad laws. So the question is, does our eval monad follow the monad laws? And let's just take the first one here. So if we do return X and bind it with F, then according to the first monad law, that should be the same as Fx. So if we try this here, I mean, just as comments, so return X, F. So return is pure, and pure is capital pure. So this is capital pure X, F, and bind is just bind. So that is bind pure X, F. And that's supposed to be Fx. But it's not. I mean, okay, fine. We could specialize it more. For example, we could use F as the identity or something. Or I don't know, whatever. But I mean, we see that obviously it's different because I mean, this uses the bind constructor and the pure constructor, and this does not. So they are just syntactically like different values of type eval. So it's not the same. Right. And the other two monad laws, it's also easy to see that they just don't hold. I mean, it's just different data. I mean, this is like a tree type. I mean, it's just a data type with constructors and so on. And those values are just not the same. But in a monad, they should be. Now, of course, if we use our interpreter from eval, then this value here will actually be converted to X bound to F in MTL. And in MTL, monads are monads. They do satisfy the laws. So then in MTL, it would indeed be fx. So after we apply the interpreter, the laws hold. So they may not hold in eval itself, but after, I mean, terms that should be equal according to the monad laws are not equal here on the left-hand side, but after we apply from eval, they will become equal here on the right-hand side. So in that sense, one could say maybe it doesn't matter, because if I always interpret these expressions in this eval monad into a proper monad that does where the monad laws hold, then it's basically unobservable that, I mean, in between I have these inconsistencies, because in the end everything works out. So that is, I mean, one could argue like that, and in some situations people also do argue like that. And I mean, there are famous examples of famous monads where the monad laws actually don't hold. For example, I think in this gen monad in QuickCheck isn't strictly speaking a monad. So the monad laws don't hold there either, but somehow they do hold in a weaker sense, that up to probability distribution or something they do hold. Right, but nevertheless, it's, so that means, okay, in this case, it's probably fine if we just use our eval monad like this to interpret it in MTL, then it's fine. But that means for each other use case, if we now write a different interpreter or try to do something else with our eval type, we always would need to think about it, that, I mean, the monad laws don't hold, and does it matter in this case or not? So now the idea is to modify this eval type a bit so that the monad laws actually do hold automatically. And the idea here is, maybe that's good to see in the slides. So this is now where free monads come in. And basically, I mean, one way to look at the monad laws is that you can always convert every monadic computation, even if it has like nested do blocks and all sorts of stuff, into this form. So you have a couple of binds. So you have one computation, bind the result to some variable. Then you have a second computation that can use this variable and do something else, get a result, and so on and so on. And I mean, couple of computations. And finally, you can return the result, which can use then this x1 to xn and doesn't do anything monadic anymore. So that's one way to look at the monad laws, that they allow you to always normalize every monadic expression into this form. And what that basically means is, if we just look at this step one, we can basically convert this whole block. I mean, we can look at it as follows. We do something monadic, and then given the result x1, we can do the rest, where the rest is again of this form. So basically it's one monadic step and then a computation that can use the result of this first step to get to a final result. So it's always like a monadic step and a continuation that, given the result, gives me the final answer. So now this is, I think, maybe the biggest leap now. So, and we should look at this, for example, bar lookup. So instead of doing it like this, so it just gives me an int and stops, so that's just a one step, we do the whole thing. So we say, okay, given a string, and so let's imagine this is this var lookup. So we would get an int, and then the rest here can use this int, do something else monadic, and return a result. So all of this is a function from int, the result of the first step, to our overall result. So what we can, so we can put it like this. We can say, so given the result of the variable lookup, the continuation that is some other monadic computation. This whole thing is a possible computation. So this is the special case, basically, this line, where this first line here in the normalization would be var lookup. So if the step 1 is var lookup, then we get an int, and using this int, there's this rest. The rest is so it's a function from int, the result of here, to the rest, which is again in the same monad. And that's it. That's the whole program. So we do the first step and the rest. So this is this line. And we can do the same for var set. So, I mean, if we do exactly the same, we would say, okay, given a string and an int, then the result would be a unit. So if we have a continuation from this unit to some eval a, it gives us an eval a. But of course, unit is always, I mean, there's only one value, so we can simplify this to this. And right, and now the cool thing is that then we don't need the bind anymore, because the bind is now implicit in this here, basically. I mean, we bind here, we do the var lookup, and then we bind the result, the int, to the rest. We do the setting, and then we don't have a result, and then we do the rest. So var lookup, I mean, we can start either with var lookup or with var set. We start with var lookup, we get an int and continue, and if we get a var set, we continue with this. And we have these error cases, this unknown var and diff by 0. So we could do that the same way, but we don't really care about the result. So therefore, we don't have this form here. But now if you look at it, we are back to where we started originally, that we have an eval a for all our constructors, which means we don't need the GADTs anymore. We are back to like standard territory, because now all have the same result type again. That's converted back. So given a string and a continuation. And this. Right. So it's simpler because now we don't need GADTs anymore. It's more complicated because now we have these continuations dangling around. Okay, and now of course nothing compiles. I mean, we have to change stuff and see it in this form. So again, basically the idea is that instead of having this bind explicitly, we bake it into our constructors. So the bind is like implicit here and here. And the error cases are special cases. Right, don't need that. That's also in the slides. Right, before we do the interpreter, I mean, we definitely have to delete this case because it doesn't exist anymore. We should get millions of errors. Here's parenthesis missing. Right. Okay. Before we do the interpreter, let's first do the these helper functions. So this is okay. This let me just comment this out quickly. I want to see error messages. Luckily, I mean, everything else still works as before, so that's good. So all we have to do is fix the interpreter and these. but someone confused it shouldn't come. Yeah, they are still errors. Right. Okay, fine. Let me just make that simpler here. Don't have to worry about that anymore. Okay, yeah, this we have to fix. Let's see. So var lookup now. I mean, I want an eval int, but now I must, so let's say s. I can do var lookup s, but now I also need this continuation. So once I have the result of the var lookup, the int, how do I then eventually get to an eval int? What do I do with the result? And in this case, it's easy. I just return it. Right? So I don't do anything afterwards. I just, once I have looked it up, I already have an int and I just return that int. So I can use pure for the continuation here. So var set sn. So I use var set sn, and then, so after I've set it, I just want to stop. So I don't make use of the continuation here. I do make use, but I don't do anything. I just do a pure unit. Right. So this compiles again. Now, of course, I still need this from eval, the interpreter. So let's see. So the error cases are easy. Var lookup now, of course, has a different argument, the continuation. So what do? In MTL, I do the var lookup, and now in MTL, of course, I do have bind. So now I need a function from in to MTL eval. The k is function from in to eval. So I do the same as I did before. So I just do from eval k. Right, and var set. So there I also have a continuation now. So I do MTL var set. There is no interesting result. And now I just recursively call the continuation. And it works. Okay, now, of course, this is now the interesting part. How do I do the bind? So this gets now more complicated. So I must now really implement this for all the cases. So let's start. And let me just rearrange this and put this pure case on top. And here as well. Doesn't matter, it's just easier to deal with pure in the beginning. Okay, so now here we don't have the bind anymore, so now we must do this explicitly. So the first, sorry. No, just wanted to give the type signature. Right. Right. So now we just do one equation per case. So the first case is pure. So we have pure A and the continuation. Well, and we have the monad law. This is this one, pure is return. So we know what it must be. It must just be the continuation applied to the X. So I can just write that here. Maybe I should have written X. Okay, fine. Okay, now the next case, diff by zero error. There we don't care what comes next because diff by zero error is an exception. So we can just, it's again diff by zero error. What's next? The unknown var, that's very similar. Again, we can ignore the continuation, so it's just unknown var. Okay, now more interesting, var lookup. So var lookup s k. So this is like the continuation that was baked into the var lookup, and but now we have in the bind we have a second continuation. Okay, and now the idea was, of course, that the K already is a continuation, right? So now var lookup is the very first step. We get the result, and then we do this. And now afterwards, we also do the K prime. So this will again start with a var lookup of the same variable. And now it's just, so let me see. So if we have n, then we would just apply the continuation to this n and then bind the K prime. Sorry, here I forgot the name. I'm not sure whether one can write that nicer. Yeah, one can, of course. I think in the slides it's written more compactly, but maybe like this it's clearer. So I mean the idea is of this normalization, we basically that every monadic compute. Let me look at this again. So the point is every monadic computation can be split like this. So we always have like a first step, and the step in our case is one of these things that we can do. And I mean, if the first step is var lookup, and we continue a bit, and then we continue a bit more, then in the combination, of course, the first step is still var lookup. And now the question is just what do we do afterwards, after we have looked up this variable? Well, we do the K and then the K prime, and that's what this says. We do the K and then the K prime. And var set. See, so we have var set SNK K prime. So we do var set SN. And now we do our K and K prime. And here now it tells me how I could have written it much nicer. Yeah, maybe I ignore this. Okay. Right. So this is a bit more work, but fear not. I mean, we will simplify that, or at least we will only have to do that once and for all and never again. But now everything should work again, I hope. And our test should still work. Okay, so we still get the right result. And I mean, it looks more complicated than before, but the advantage is that this is now actually a monad that does fulfill the monad laws. So I don't want to prove that, but it's relatively easy to prove that all the monad laws now hold. I mean, this first one, for example, by construction, because of the way we implemented this. So this obviously holds, and the others one can also easily check that they hold. So now we have like a way to turn these abstract thingies. I mean, basically that was completely arbitrary. I mean, we just say we want a monad with certain operations, and we have turned it into, I mean, we have constructed one. So what this says is we can basically give a bunch of operations and then construct a monad for it. So we had to basically add this pure constructor to the stuff we want. And then we had to like work quite hard to implement the bind. But if we do this correctly, then it's possible.
Lars, there are a question.
Yes. Yes.
Tony have a question. Could you repeat the reason why we include the continuation in the constructor?
Right. Yes, the idea is that we want to get, I mean, in the version before we had the bind constructor explicitly. And that is basically the reason why the monad laws don't hold, because of this bind constructor. I mean, then you can easily implement stuff, but it's not lawful monad. And the observation is that you don't need bind if you normalize it like that. So the point is that in any monad, I mean, or let's say in this particular monad, we know no matter what you do in eval, you always start with one of those four things. I mean, either you immediately return a result. And if you don't immediately return a result, then you do one of those 4 things. And I mean, these are somewhat special. So, I mean, this is like the most typical thing. So, I mean, you do, for example, a lookup first. I mean, you must start with something. So, for example, you start with a lookup. And the observation is that, I mean, then the lookup, I mean, all you can do afterwards is bind to the result. I mean, you can either, I mean, you get an int and then you continue. I mean, that's exactly what bind does. So it allows you to string several computations together. So you have the first one and the rest. And this here is basically the rest. What you do with the int that you get out of the first step. So you have a first step and then the rest. So there's basically the idea why we add the continuation is that earlier we just had like these separate steps, the isolated atomic operations. But in order to be able to do like 2 steps, we needed explicitly this bind constructor. By using the continuation, we can do, I mean, the whole computation using one constructor. So basically now the constructor says what's the first step. So the constructor now, I mean, before, if we want to do like 2 lookups and a set, then we had basically a lookup, I mean, bind, lookup, bind, I mean, lookup, bind, lookup, bind, set. So we need to use the bind constructor twice. Now, I mean, the whole thing would just be one var lookup. And then in the continuation, we would have the second var lookup and then eventually the set. So by this normalization, we don't explicitly need the bind anymore because it's always like one step and then the continuation is bound to the result of that step. So it's implicit in the continuation, if that makes sense.
Say, why then do we double bind in the implementation of bind?
In the implementation of what? Sorry?
The line 22, I think. Yeah.
Right. I mean, what's the meaning of this? I mean, this is supposed to mean we do a lookup, we take the result, and we then apply the continuation to the result. And this is exactly what I do here. I mean, if I interpret it, I must interpret the lookup. I get the result. Then I apply the continuation to the result. So I get another eval A. But I mean, I need an MTL eval A, so I recursively apply from eval to the rest of the computation. So basically, I deal with the lookup like this, and then recursively do with the rest with the continuation like this. And of course, in MTL, I mean, it's bind. I mean, that's the point. I mean, here it's implicit. I don't have the bind constructor now anymore, but of course, I mean, that is like an actual bind in a monad. So if I interpret it in another monad, I express that with bind. I mean, that's exactly the idea here. What this is supposed to mean is look up variable s, and if you get an int result, continue with k. So k takes this int result and continues with it. And that's exactly what I'm writing here. Look it up, you get an int, and then, well, apply the continuation to that int. So you get another eval a, and recursively you also translate that into MTL.
I think Tony wants to add something. Tony,
Okay.
go ahead, please.
Yes, can you hear me?
Yes, I can.
Yes. Actually, I meant by the double bind. I meant in the implementation of the bind in the monad down there.
Yes.
So you see that if you look at under var lookup, you
Right.
actually we apply the k which was a continuation, and then again we bind a k prime. So there's kind of an idea of double bind.
Right.
It's a bit confusing.
Right. I mean, what does this mean? That means first look up variable s, and then continue by applying k to whatever you found. I mean, if it was 42, then apply k to 42, and that's how you continue. But now we are supposed to implement bind in our monad. So we have this, and now we must be able to, I mean, because it's supposed to be a monad, we must be able to bind it to another continuation, k prime. So what it means is first look up s, then do k prime. and we basically define bind recursively. We say, okay, fine. The first step is still the lookup, of course. I mean, this is basically like a re-bracketing. I mean, here it's like, I mean, it's a bit like var lookup sk lookup as sorry. Almost like this, but this wouldn't compile. Therefore, I mean, it's a bit because of this end. But anyway, I mean, that's the idea. I mean, we are given this. So start with a lookup, then do k. And now the question is, okay, and what happens if you do this and then afterwards still want to continue with k prime? I say, okay, fine, that's easy. You still do a lookup, but now your continuation is different. Now your continuation is not just k. It's first you do k and then k prime. So I basically just shift the k prime into this continuation. I make this one more complicated because I need it in this form again. I mean, I need an eval b. So as eval b, I mean, I have to, I mean, I need to use one of the constructors. I mean, this is like only in, I mean, this is not correct, of course. I mean, it's like I mean, morally, it's like
Thank you.
this. Welcome. So, I mean, it's actually, I mean, apart from like noise, it comes from like lining the types up. It's actually quite simple. It says if I mean, I have a first step and the second on the continuation, and then another continuation. That's the same as having this first step, and then like as continuation just like slap together these two. And how do you slap them together? Well, like this, where this, of course, is a recursive call again to the same bind. So this is a recursive definition. But I do make progress. I mean, it's fine. I mean, it won't loop forever because now I have produced one step. I know, okay, if I bind that, I still have to start with this var lookup. And then, I mean, I recursively have to see. I mean, depending on what kn is, I mean, can be another lookup or var set. So, right. But that's how I mean, that's the idea. Right. And I think this is like the most tricky step. And of course, it looks not very, I mean, it's cool, I suppose, that we are able to create a monad like this. But of course, it's I mean, it's quite complicated. And if one always had to do that, that would be a bit painful. I mean, but it's already cool that it's possible to do this. That you can basically write a monad from scratch that has like arbitrary operations. Right, and now the idea is, let me see what the idea is, how it's put here. So we did this. Right, I did this. Continuations everywhere. I did this. Did that. Yeah, and this is, I mean, one can, I mean, basically in functional programming, everything is a tree. And you can sort of think of this as a tree where the leaves are pures. And basically bind is given by substitution. So what bind actually does is, I mean, you imagine, I mean, like a tree where, I mean, the leaves are pures and you have like different node types for the different other constructors. And so all these, eventually it's always an eval A, which is a pure in the end. But if you now bind, what you basically do is you replace these pure leaves with like the whatever you bind against. So that's one way to picture it, maybe. Sure how helpful that is. Right, that we did. I started with that actually. So we still have our helper functions. And now actually it's not just constructor names anymore. So now it was a little bit more complicated in these cases. So now it makes more sense why we have these helper functions. And we did write the interpreter. So that's still cool. And monad law still holds. So that are also set. Right. Maybe it's time for another break. Then we look at another example. So the plan is now as follows. So this looks, I think it's cool, but it's quite complicated and it looks very like specific to this example. So now what we will do is we look at the second example and then we'll generalize and see that basically it's always the same thing. And then in the end, we'll reach it. So, get to so-called free monads where it's very easy, where you don't have to do that by hand. So basically there's a library, you just say which operations you want and you automatically get a monad without having to write all that boilerplate more or less. So yeah, but I think we should have another break maybe until, I don't know, 35.
Okay, yeah.
Okay, talk to you then. Okay, can we continue?
Okay.
Okay. Let me just do one other renaming. I think it's still too early to call that one free. Let's just move that to, I don't know, whatever, ad hoc. Um, second. I must rename it. See. Right. Okay. Maybe I don't need this. Actually, I don't know whether you have already done this exercise. I hope so. There was this GP exercise. And where you were supposed to implement a monad instance for it. And it is very similar. So where we had this pure constructor that was called end in the exercises, but return or pure was just end, same as we have here. And then the bind was actually exactly like we did it. So for the end pure case was just the continuation applied to the result, same as we did here. And then for get and put, it's again the same constructor, get, put. And here we basically chain the continuations. And that's exactly the same what we did here for the var lookup and the var set. So it seems there is like a general scheme here. And actually, so now we can do free, I think. So let me copy this just. Free. Let me rename it again, sorry. So free. 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 Yeah. Just not save it then. Fine. And this VP thing I can delete again. Free. Okay. Okay, fine. So right. So now we like slightly modify this to make it more general. So first we split this into two parts. So one part we call eval op, for example. We remove the pure and leave all the rest. And in eval, we put the pure and everything else. So we just, and we call it wrap, it's an arbitrary name, and then eval op A. Is that correct? Yes. Right. So this basically doesn't change anything, right? So we have this pure extra now, and we just have this wrap constructor like wrapped around all the others, but we still have exactly the same cases, except now, of course, this all won't compile anymore. So let me, for the time being, okay, right. Okay. I mean, this is basically, it doesn't change any information. It just moves the, I mean, here's only what is specific. I mean, the pure is like general monad stuff or applicative stuff. So I just split that into two types. And I could, of course, now, modify everything accordingly. But now the second thing is that I don't really, I mean, this eval, I can now change it like as follows. I call this, for example, B. I mean, I could also call it A again, but then maybe it's confusing. And now, of course, here, then I have to say eval, sorry, yeah, eval A. Okay, and finally, this here is now basically completely generic, except for this eval op here. Let me just check that I don't do right. Right. So now, and then last step is that I make this here completely generic. So as I don't call it eval anymore, I call it free f, and replace this and define eval simply as free eval op. Now again, I mean, haven't changed anything. So this still has exactly the same information as before, but now I have like something specific to our example, to these expressions, to the evaluation, and something that doesn't mention the example at all and would work with any type constructor, like eval op. Okay, and now the idea is that I can basically implement monad just for this free. So it doesn't matter anymore that it's specifically eval op. And just as an, I mean, I don't know whether you did this exercise with the fix, how one can do recursive data types like explicitly with this fixed point operator fix. And that is like just an observation that it's very similar. So, I mean, this in is a lot like the wrap, but now we have additionally this return or pure that I called it now. So that's the only difference, but that's just like a analogy, whether that helps or not. And oh yeah, for this GP, so we had the get and put, so we could do the same thing. So we could do data GP op B. So there are only two operations, get and put. We have get, given an int, we can continue, and put, was it also an int? Yeah. Right. And now we could also say type GP is free GP op. So, and this bar is wrong. Right. So this is now a second example. So basically just giving the operations we are interested in, like eval or from the exercises is GP. Now this free constructor does like the complicated thing. And it adds the pure and it has this wrap case. Right. And now we will basically see that it's possible to implement the monad instance just for this free without caring too much what this functor is or this f, this type constructor. Let me just move that here and put it there. So now the idea is we do everything that we did specifically for eval now for free F. Right. So slowly. So this still makes, sorry, of course I have to free F. So that's fine. Here it's free F. And so this I can just leave the same because I still have the pure constructor here. So that's good. This is still fine. I must just replace the eval with free. Return. Also fine. Now, of course, this is no longer fine because this was still very specific to eval. But the first definition is okay. Now let me just so far everything should be good, I hope. Just okay. Right. So now the rep case. So we have rep something. What is it called here? Okay, I don't know. I can call it, I don't know what, F maybe. Okay. Right. And now, I mean, what is this? So, I mean, this is now like the second tricky part today. So rep is F of free FA. And let me just put a hole in there and let's see. So I need a free FB now. And what do I have? I have the F, which here, which is F of free FA. And I have something to go from A to free FB. So what can I possibly do now? I mean, at the moment, basically nothing if I don't know anything about the F. Okay, and I need something of type free FB. So I have two constructors, pure or rep. So let's use rep. So now what? So now I need something of type F of free FB. And I have something of type F of free FA and something of type A to free FB. Let me see, just a second. Okay. Okay, I have something of type F of free FA needs something of type F of free of B. Is that correct? Yeah. Sorry. Okay. Now I don't know anything about these things. Second. Okay, right. Sorry. But if the F wasn't here, I mean, I could bind, I mean, recursively bind with this continuation. So I would get something, I mean, because the continuation allows me then to go from the free FA to the free FB. So the continuation, I mean, let's say what I want to say. So sorry about that. So the K, let's just write it down. So F is of type F free FA. The K is of type A to free FB. Okay, so what is binding with K? So that takes something of type free FA and gives me something of type free FB. Okay, and this is basically the idea. Because I have something of type F free FA and I need something of type F free FB. So this looks very close, but the F is missing. So if F was a functor, then I could F map this to go from here to where I want to be. And now the point is that actually this is a functor and we don't even have to work for it. We can just do that automatically. Sorry about this, derive functor. Okay, but not used, but now we use it. Just do deriving functor. And incidentally, this is also a functor. And I think in your exercises, you were supposed to implement the functor instance. So those are both functors. So we won't be able to write this for arbitrary f's, but if f is a functor, then we will, because now we can just fmap. So fmap binding with k is now of type, because f is a functor, I have fmap to f free fb. Okay, and this is exactly what I need, because I need an f free fb here, and I do have an this f is of type f free fa, so I can just f map over f. Right. And I mean, this is admittedly complicated, but if you basically unwrap it for the cases that we had, if you compare it with this ad hoc and compare how the functor is actually, what the functor instances are for this eval op and the eval, then you will see that that is exactly what we had before. So we are really just using, I mean, what is the functor instance for this? I mean, if you have something from B to B prime, then you just compose with this. And this is exactly what we did here. We just basically compose with, I mean, this thing. Right. And this is now basically the final form. So what we have we achieved now? Okay, let's see. So this I don't need anymore. So provided that this f is not some arbitrary type constructor, but is actually a functor, we can write a monad instance for this once and for all. So now whenever we have a functor, we can do free of that functor and we get a monad. And examples are, for example, our eval is now just free of eval op, and our GP is just free of GP op. Now, of course, we want to see whether the other things still work. So let's see. So let me just So this is still okay. Now I should get many more errors actually. Let's see where the other errors are. Okay, that's one. Oh, why is there anything wrong earlier? I'm just wondering. Oh, sorry. I don't know why it's complaining. Probably I have to reload because there's no GP anymore. Just want to see the errors. Okay. Right. I mean, now, of course, that is not correct anymore because now I have this pure and wrap. So I must wrap everything in this. Really? Two? Oh, yeah. Confused now? Sorry. Oh, yeah, I think I deleted there something. Sorry. I deleted something earlier by accident. So there was a B. Right. Yeah. Now I see all the errors. Fine. So let's do one by one. So now it's wrap. So it's a bit less pretty because now I have this wrapper, but in principle, should exactly be as before. Yeah, so this was easy to fix. It just, I mean, it just needed this wrap additional constructor. So that's good. Now let's do these. Okay, now I also have the wrap stuff. And wrap. So they get a little bit more unpleasant, but now everything compiles again. Now let's see. This I can delete here in this module, I think. Right, but our evaluator still works as before. And let's see. Free monads, free test. Okay. Okay. So I mean, this is now admittedly a bit more complicated. But I mean, substantially nothing happens. I mean, it just looks noisier because of this constructor. And but like, I mean, there's nothing. I mean, the right-hand sides are still the same, so it's not really more difficult. And these helper functions now also have this additional wrap. But now what we have the monad instance for free. So that would be one way to explain why it's called free monad. So something like that is called a free monad. So you start with a functor, an arbitrary functor f, and then free f is a monad, and you get the monad instance for free. So that's one, because I mean, we have written this once and for all now here. And that means for arbitrary functors, now you immediately get a monad with this free constructor, free construct, yeah, type constructor. And but that's actually, I think, not the reason why it's called free monad. Free is something from category theory in mathematics. So it basically means it's a monad that adds only basically the least necessary things to make it a monad. So it's free in the sense that it's only constrained in being a monad. I mean, apart from being a monad, it's completely free, if that makes sense. But you can also just think it's monad for free. Okay, let me see. Free. Right, they are functors. Okay, so far so good. So this is now, apart from monad transformers, which allow us to basically, given a monad, to produce more monads by applying a monad transformer to it, we now have like a second way to produce monads automatically. I mean, without writing instances by hand. Namely, if we have an arbitrary functor, then we can automatically get a monad. And but I mean, the use cases, of course, are different. So for monad transformers, we saw that we can basically plug and play effects. And free monad is this interpreter idea. So you basically define the operations you want, and as long as that is a functor, you can turn it into a monad. And then you can write programs in this monad, and then later have one or more interpreters that actually do something useful with it. But because it's just this concrete data type, it's possible to like analyze those programs or inspect them basically. So it's like a program as data, and then later you have different ways to interpret it. And I mean, one way to try to get a feeling for free monads is to ask what it does for certain well-known functors. So for example, if we look at the const functor, remember const AB basically holds a value of type A, and the B is completely arbitrary. And it's a functor. We just ignore the B. I mean, a function from B to B prime, we just keep the same A that we had. I mean, we looked at const, we used that excessively when we talked about optics, for example. So const A is a functor. So the question is, what is free const A? I mean, we know it's a monad, but is it like something totally new, or is it like a monad we know? Or, okay, what is free const unit? And if you write down the types, so we have return or pure from A to that thing, whatever it is. And we have wrap. So if we just write the definition down of wrap, so it's by definition given a const unit of this monster, we get something. But const unit, I mean, this is just, I mean, doesn't matter. It's always something of this type wrapped. So it's just unit to here. And this is basically the same as this, because unit doesn't matter. I mean, a function from unit is always just that thing. And this shows, I mean, this actually, does anybody has a guess what well-known monad that is? I mean, you basically, all you have is like these two ways. So there's like one specific element here that you get from wrap, and then there's this return. So you can take an arbitrary element A into this new monad, and you have like a specific element independent of A. So it turns out that that is maybe A. So free const unit A is the same as maybe A. I mean, not syntactically the same, but you can write maps back and forth. So just is just return and nothing is wrap. And so this is basically one way to recover the maybe monad. So the maybe monad is a free monad. It's free monad of the functor const unit. And I think we haven't talked about void before. So void is a data type that doesn't have any values. So it's empty, it's void. I mean, unit has one value, exactly one. Void has no value. And so we can also ask what is free const void. So I mean, we could do the same calculation here, and then instead of unit to free const void A, we have void to free const void A. But there is no void, so we can not apply wrap to anything because it's void. So that means the wrap constructor is not available. I mean, it's available, but we can't apply it because we don't have a value of type void. So we only have pure or return. And that means this is the identity functor, the identity monad. So free const void is actually the identity monad. So we can recover maybe and identity, two well-known monads. I mean, they turn out to be actually free monads. Right. And let me just see what's afterwards. Right. So there's a nice example. Let's just see. Okay. So the free construct allows us to give an arbitrary functor to immediately turn it into a monad. And the functor basically describes the special operations that this monad has. And values are just terms, so that monad doesn't do anything. It's just a data structure. And you can, I mean, if you think of this data structure as a tree where the leaves are pure values, then bind basically is substitution. So it applies the continuation, what you bind against. I mean, it basically replaces the leaves with like the trees that result from the continuations. And the advantage is that because it's just data, such a computation, you can analyze it and you can write different interpreters for it. And disadvantage is that it's very inefficient, actually, the bind, and that is similar actually to why concat for lists is inefficient, because you have to basically shift all the parentheses like to the other side when you calculate it. That makes it inefficient. However, there are tricks to make it more efficient. So there are like slightly more sophisticated or like formulations of this free monad idea that make that problem go away. And there's incidentally, just see, sorry. There's a package on Hackage called free. I make it larger now, which amusingly is called monads for free. And it's also, I think, by Edward Kmet, who is also the author of the Lens library. And he basically has like an implementation of this more performant way. And there are also like other things. You also have something like free applicatives and free alternatives and whatever. But particularly there is control monad free. And what was the examples? And this is a bit right. Data free. Okay, and he doesn't call it wrap, he calls it free. So what we called wrap, he calls free. But apart from that, it's the exact same definition. Right, and there are lots of stuff, what you can do with it. So yeah, you don't have to do that by hand. I mean, you can use this this package. Okay. And if you recall the exercises, so for this GP monad, there were two interpretations. So one was as IO action and one as a simulation where the inputs came from a predefined list and the outputs were collected in a list. So, I mean, this is basically, and I mean, in the exercise, you didn't know it was a free monad, but you already saw that you could write programs using this GP and then, I mean, the same program interpreted in different ways, like in IO or in something else. So that's basically the main advantage of this. You can have a monad with abstract operations and write programs in it, and then later decide how to interpret them, if you want to interpret them. And I mean, for eval, we only saw one interpretation with the monad transformer stack. But we could, of course, also, like, for example, not use monad transformers, just do it by hand, similar to this monad error, or what was it called, error state from the exercises, or some other way to get the desired effects. And are there any questions? Because if not, then there's a nice different example.
No, I think no questions so far.
Okay, good. Then you see it and look at a nice example. Let me just see that I don't know. So let's call it concurrency or something. Thinking too much about monads. Module 3 monad. Concurrency. Actually, I think it's a bit stupid that in the slides it's called rep, because it's called free. So let me just rename that to free, okay? So that it's like in the libraries on Hackage. So let's forget about rep. Let's call it free. Okay. Right. So here the idea is that, of course, we had a lecture, at least one lecture on concurrency in Haskell. And this is basically what if there wasn't, if it wasn't built in. So could you basically implement concurrency yourself? So I'm not talking about parallelism, so not several cores, just basically switching between like threads. And this is like a nice example, I think, very nice example how one can simulate concurrency. And the idea goes back to Kuhn Klaassen. And right. So first we need our operations. And what are they called? Okay. Okay, let's do this. So I need GADTs in this example. So first we need these operations that we want, and that must be a functor. So in this case, it's called process op. I can also call it A in the slides. It's R for result, doesn't matter. Okay, and we want two operations. First of all, we want to be able to embed IO. So we want to do IO, arbitrary IO. We call that atomically. Let me call it R, sorry. So if we have IOA, and then somehow given the result of this IO action, we want to get to the result, then that's one way to get a process op R. And because we're talking about concurrency, we want to be able to fork. So if we have, process is not defined yet. So process will be, process is free process op. I must import this. Okay. So and given a process, I want to be able to fork it. And then R is the result of my, or the continuation of my main thread. And that's another way to get a process op. Sorry, unit. Okay, so that's the two operations that I want. So either I want to be able to do I/O, just normal I/O, and I have the continuation, so turning the I/O result into the overall result I want. And secondly, I want to be able to fork processes. And so I fork the process, and this is basically the result of the main thread. That's the second operation. That's the two atomic operations I want. And atomic is a bad word. I mean, the two operations I want in my monad. So now, in order to make that a monad, I need functor. And nice, of course, that. So deriving functor. Sorry. Okay. Okay, then I have to. I just want to see how the slides do it. They don't do it at all. Sorry. They don't. So the slides ignore this problem. The problem is if I try to derive functor, I get this error message. Can't make a derived instance of functor process op. Constructor atomically has extensionally type variables in this type. Right. The problem is this A here. I mean, this is called an existential type variable because this A doesn't appear anywhere here on the right. And something like that is called an existential type variable. So that means if I have a value of type process op that uses constructor atomically, I know that, I mean, whoever constructed that value had some specific A, but I don't any longer know what A that was because it's, I mean, it doesn't appear here in the result type. That's why it's called existential. Anyway, so I can't derive, but there is also a hint given. Possible fix, you standalone deriving. That's something you also don't know yet, but it's basically just another syntax for this deriving. So instead of what we always did in the data declaration, write deriving whatever, one can also write something like this, deriving instance functor process op. So that's the syntax. And for that, I need an extension called standalone deriving. So instead of putting it directly into the data declaration, it's basically a new top level thing. It starts with the word deriving, then instance of what and what. So, I mean, if we wanted to implement it by hand, we would do something like this, right? Instance functor where, and of course we could do it by hand, but instead we can use this, and that's called standalone deriving because it's standalone. It's not part of the data declaration. It's standalone, like top level thing. Right. So it's a functor. So we know process is a monad because of the magic of free monads. We automatically get that now. And now we can write programs in it. So I don't know what the example was, but it also doesn't matter. So let's say program process. So I can, for example, on one thread, I mean, I could write programs in it, but before I do this, I mean, what we did before, I mean, it's a bit awkward to work with these directly with the constructors. I mean, we could, but it's better to have like these helper functions, what we also did for our eval monad. So let's write those first. So we want something called atomically. Just takes an IO action, turns it into a process of the same type. So for that, of course, we use atomically, but we have to wrap it in this free constructor. So free atomically. So we need our action, so M, and we need the continuation, how to turn the A into the result. So in this case, we need an A into a process A, and that of course we can just use pure. So that's that, and we want to be able to fork. So process unit, process unit, fork P is free fork P. Now what do we need here? Reprocess op unit, so we can just use pure unit. Okay, and with that out of the way, now we have our helper function. So process is now the free monad that has these two special operations, but they don't do anything. I mean, the names of course suggest something, but there is no interpreter yet, so there is no concurrency implemented yet, of course. Just to demonstrate that we don't need that in order to write programs. Now we can do something like fork replicate M. Just import this 5 atomically string line Haskell, and fork replicate M7 atomically string line, I don't know, Nairobi, and replicate M3 and the string line Kenya, for example. So the idea is I fork 2 threads, one that prints 5 times Haskell. I fork another thread that prints 7 times Nairobi. And then on the main thread, I print 3 times Kenya. And of course, this doesn't do anything yet. So we need an interpreter. And I mean, that's, I think, quite a very cool idea. So, right. And the idea is that our interpreter has the following form: schedule. It takes a list of threads, of processes. So that's a list of threads, and runs it in I/O. So simulates basically concurrency. So runs these concurrently in I/O. And I mean, we can do that without having concur. I mean, we could, I suppose, use it with. I mean, we could use fork I/O to actually use threads, but I mean, this is about simulating concurrency. So I mean, if there's no thread, then we are done. So we don't do anything and the program stops. But if there is a first thread and other threads, potentially other threads, well, then it depends whether it's pure or free. So now we can pattern match. And this is now the point, I mean, where we see that or one of the points, I mean, we can inspect. So if it's, sorry, a pure, and in this case, because they are all return type units, so it must be pure unit. Yes, let me just check whether I do this right. Yeah, I do. So then, I mean, this doesn't do anything. We can just drop that thread. We are done with it. So we just recurse with the rest of the threads. Okay, and then it could be a free, well, now we have these 2 constructors, so it could be atomically. So it's some IO action and a continuation. Let's call it IO and K. and then of course the rest. So now the idea is that we perform this IO action. So we get an A as a result. And now we have this K, and okay, so now we have the continuation. So after we have the result, we are supposed to, we have to continue with the continuation. But the idea of the scheduler is now this first thread had a chance to run. So now we want to give the other threads a chance. So the continuation, we won't forget about it, but we will like schedule it at the end. So now we will recurse with schedule, and we first do the other threads, and at the end we now add the new thread the continuation of A. I think that, yeah, I hope that's still good. Distinct. Just want to see that I don't make a mistake.
I think you need to save the file.
You're right. Thank you. Okay, but it does compile. It just tells me that I missed cases, obviously. Right. So idea is here, if it's an atomically, I execute the IO action, remember the result, apply the continuation to it, and then schedule it at the end of the other threads, so that the next thread will get a chance to run. Okay, and the final case is if I have a fork. So I have free fork P K, whatever. Yes. Okay. What do I do in this case? The K, what is the type? Okay, that's just one of these things. Or I could call it Q maybe. Okay, so now idea is again that, I create a new thread now for this P and one for the Q. So now I have several choices how I schedule that. I think in the slides, let me see. Okay, it's, so I don't even need this. It's schedule. So I first run the other threads and then the continuation on the main thread and the new one, the new fork one. Okay, and that's it. So this is the idea to implement a simple scheduler. The idea is, you have a list of threads that are supposed to run concurrently. If the list is empty, you are done. If the first thread is done, you drop it and continue with the tail. If the first thread is an IO action, you execute the IO action and then schedule the rest, the K, the continuation at the end. So now basically this first thread had a chance to do a step, an atomic step. Now the others get a chance, and this one is scheduled at the end. And if it's a fork, if the first one is a fork, you basically schedule the continuation of the main thread and the newly forked thread at the end. I think the order here doesn't really matter. You could also write PQ or whatever. But that's one way. And now we can try this out. So we had our program. So we can do schedule program. So we start with just one thread, just the program. And it does this. And it leaves it nicely, reasonably. So we see what was the program? Okay. Yeah, that's that example. And we should get 5 Haskells and 7 Nairobis and 3 Kenyas somewhere. Kenya. 1, 2, 3, 4, 5. And the rest Nairobis. So yeah, I think that's a cool example. And you could, of course, actually, if you ever apply to IOG as a Haskell developer, I happen to be the one that posts I mean, there's a test that you're supposed to do like at home, write a program, and that is actually very similar to this example. But I mean, in this test, you're supposed to write two, I mean, interpreter as well. I mean, this one, but in I/O, but also basically a pure one that simulates all of this, not in I/O, but I mean, of course, then you don't have this atomically, so it's a little bit different, but similar idea. And also, this is very, I mean, I love that. I think it's very cool. I mean, these basically simulated, I mean, simulating concurrency and so on. I mean, this is relatively limited now because here we don't have anything like MVARs where threads can communicate with each other, but you can also easily add operations here, for example, channels, that you can create a new channel and then basically send something on a channel or receive something on a channel, and also extend this then that the threads can basically send each other messages. And that's actually quite cool. So you can, with this message passing style, you can, I mean, you can do it in I/O, and then it's like an actual distributed application that you could run in production, but you can also do something similar to this, a bit more complicated then, of course, because you also have to keep track of these channels and what's in them and so on. But you can basically simulate that. And that's actually also similar a bit to what I mentioned earlier, the SimIO, what IoG uses to test our code, like for the Cardano node. I mean, this is also similar. That basically they simulate concurrency like that in a pure deterministic state. So I mean, this is like poor man's concurrency. If it wasn't built into Haskell, using something like that, one could actually write concurrent programs that I mean, that just all run on the main thread, of course, but still simulate this scheduling. That, I mean, obviously here, I don't know what the technical term is, but I mean, here, if this atomically block, this IO action takes long, then it will just, I mean, basically what's it called? I don't know. But there's a name for that. So basically a thread has to voluntarily yield control, and then the next one gets a chance. Whereas I think in Haskell, for example, I mean, if there was a like long running action, then the Haskell runtime can forcefully interrupt it and give another thread a chance. So I mean, it's not, of course, as good as the actual runtime system, but nevertheless, I think it's quite a neat example. Are there any questions at this point?
I think no questions so far. Yeah, it's a cool example. Yeah.
Maybe I mean, to come back to I mean, because we still have half an hour, and I mean, as you know, one of my favorite examples is this probability stuff. So that's actually also a nice example of free monads, or can do it as free monads. So maybe I can do this. Monads, where are we? Right. I mean, I did it a little bit different there. I did type classes, but you could also do it with free monads. So I mean, like prop op. Um, not sure I need GLDTs, probably not. Right, and I mean, basically all I needed was this coin flipping with a given probability. So coin given a probability, it gives me a Boolean, I mean, true or false. And this here is basically the probability. So all I want is this special operation coin, and then given a way to turn a Boolean into the result, I get a prop op A. Right. And for this, I indeed wouldn't need GADTs, so I can write that in the normal way. Sorry, like so. Okay, and this is also a functor. Okay. And now, I mean, the schema is basically always the same. So first you define your operations, then you define helper functions for you instead of the constructors that you can easily import this free monad stuff. I mean, normally, of course, you wouldn't import it from this module, but from a package like Quet's free package. Now I can define type prop is free prop op. So now I know this is a monad, and now I can define my lowercase coin. So given a rational, it's a prop pool. And okay, so it's the free constructor, then the coin constructor. Sorry, the probability P. And now I need continuation of type bool to free prop op, so that's pure. I mean, you see this is always following the same schema actually. So if you have done that a couple of times, these are just boilerplate. Okay, and now we could write probabilistic programs. So if I remember, does anybody remember when I did that, where that is? The example I had back then? 9 probably.
Maybe data structure, I think. Maybe.
Okay. Which week is that? Sorry. Section patterns was monads. That's right. Yeah, you're right. 14 or 15 probably. Yeah. Okay, it was this one. Let me just open that. Cause let's close some stuff. Okay, fine. Because I had this thing with the random int, so I can just copy this now. I mean, back then I had defined this monad prop thing. Now I don't need that anymore, so I can just say int to prop int. But the code is exactly the same. Yes, the code is exactly the same. So there's actually a very, I mean, I should mention, I think that's also not mentioned in the slides. I mean, these free monads are very nice, but what I did back then, because I didn't have free monads, I did this this class that I defined with this operation. And this is actually, in a sense, more or less the same as free monads. So the one is called, I always forget, I mean, one is final and one is initial. So it's like two ways to do this. One way is to basically define a class, like I did back then, my monad prop, which with all the operations you want. And then, I mean, an interpreter is then basically just writing instance for this class. And another way is free monads, and then interpreter is like a function from the free monad to like a concrete monad. And in some sense, those two approaches are more or less equivalent. So one can write I could write an instance of monad prop for my free monad prop now, and I could also somehow recover this class thing. But anyway, so it's more or less the same. So it's no wonder that it's very similar. But anyway, so we have this random int now. And now I can also, for example, have one die. So it's prop int. So this gives one from 0 to n. So I want one from 0 to 5 and add 1. Okay, and I could have like 2 dice. Up int, comma int. Okay, so I mean, this is just going to show that as before, I mean, it's a monad and I can write programs using it. And of course, now, I mean, it doesn't do anything. At the moment, it's just data. So now I would write interpreters. So if I, for example, want to write prop to IO, so prop A to IOA, prop to IO pure A is just pure A, and prop to IO wrap. And before I can do this, I need the random package. Let me reload. And actually, I mean, I did have this interpreter earlier. I mean, back in that example, how I made IO an instance of this is here. And this is basically now exactly the code I will need now to implement this. Let's see. Just copy it here. Okay, so wrap coin p continuation. And it's not called wrap anymore. I changed the name to free. Yeah. Okay. So now I can basically, I mean, what's the P and what's the K? So P is rational and K goes from bool to K. So I want it to be in IO now. So first I need this Boolean. So this is exactly this. So I can basically copy this code, first of all. Sorry.
To block, I think.
Yep. I must import that. Right. And so this is now the Boolean basically. And now, of course, I mean, this is a Boolean, but now I mean, I have this continuation and I must get to A. So I can apply the continuation to the Boolean. And now I'm in prop A, and now I recursively do prop to IO. Right. So it's basically almost exactly the same code. Just going to show that this, I mean, free monad is sort of like, I mean, it's not really something fundamental. I mean, it is something new, but it's very much related to this other approach, this type class approach, as you can see. Right, but now I have my interpreter from prop to IO, and now I should be able to did I call it run a prop? Okay, and now I should be able to, for example, do prop to IO dice. Why not? Why? Two dice.
Two dice, yeah.
Two dice. Right. Okay. And of course, it's only fun if you have at least a second implement. And now actually, I mean, there's now one thing that is actually nicer with free monads with this approach. I mean, earlier in the example I gave you some weeks ago, I had this dist A for like to give you the complete probability distribution. And that was, I mean, defined like this. So lists of A's and rationals. And then, I mean, we wrote a monad instance for that. So all very well. And then I had this summarized thing because, I mean, with the list, the problem was there was lots of duplication. So we got like for like 2 dice, we got list of length 36 for each of the possible combinations with probability 1 over 36. So it was difficult to see that, for example, and for example, the sum of, actually, sorry, I think 2 die was different. It was not just 2 dice, it was like the sum of 2 die. So let me change this to plus, and that was, yeah, that was the example. So it adds the 2 die. Right. And I mean, of course, I mean, it's well known that 7 is the most probable one. But I mean, we had this list representation for probability distributions, and then, but it wasn't, I mean, it had duplicates. And then I wrote this summary function, summarize function, which takes such a list and folds it into a map. Right. And this is now one nice thing maybe about, or relatively cool. I mean, we can do the same, but we can do it like somewhat nicer, I suppose. We do, I mean, this interpretation, they don't necessarily have to go into monad. I can also go into whatever I want. So for example, I can now write something like whatever I call it, prop pure, which takes a prop A and directly gives me a probability distribution. I don't have to worry about a monad instance for this or anything. So I can just go to map A rational. The only thing, and now I of course need an odd constraint on A. And I have to import this, of course. Control monad. Sorry. Data map. Modified as map. Okay. Yeah, this is actually my, I think, a nice example of an interpreter, because I mean, normally, I mean, often these interpreters go into another monad, like we saw in our MTL example. I mean, we had this MTL eval monad and our free monad, and then the interpreter goes from the one into the other. Same with IO, same like now, just here. So we go from one monad into the other. But map is not a monad. But nevertheless, I can write an interpreter. So let's do this. Okay, again, of course, the same 2 cases. So if we have a pure A, so what should that be? What map? Well, it's the singleton map that only has one entry, namely A, only one key A, with probability 1. So it's map singleton A1. And prop pure the other case. So I have free coin PK. So let's see. What is K now? Right. And now let me think. Okay. Okay, fine. So this tells me what happens if the coin flips to true or to false. What should I do then? So let me just write that down. So and I mean, in the end, I want a distribution of A's. So the K gives me basically, I mean, it's a function from bool to this. So basically what that says is it tells me the distribution in case I throw, I mean, I have heads and I have tails. So let's call that whatever. I don't know. D true or something. So that's K applied to true. But actually, I mean, this is now again in the monad in prop A, but I want the distribution, so I can recursively apply prop pure to it. And defaults is prop pure k false. So this is now two distributions that the continuation gives me. What the distribution of A's will be if the coin flip is true, and what the distribution of A's will be if the coin flip is false. And now I just have to assemble those two to a joint distribution, basically. So what do and that means I must basically add them, but weigh them with P. So because the true case happens with probability P and the false case with probability 1 minus K. So I have to somehow combine the two maps. And I'm sure there is something appropriate, or maybe not. I think it's called union with. Yeah, right. There's map union with. So that gives me two right. Let me just think. No, I think that's not right. No, first sorry. First I must scale them accordingly, and then I must add them. Sorry. That's fine. Yeah, this is correct. Let me just write it down. Union with plus. And now I have to the D true, but I have to scale it with P. P times or time, yeah, P times D true. And the other one I have to scale with 1 minus P. Right. Okay, so again, I mean, it's like a bit backwards now because we always have these continuations. So the P is the probability that my coin flip will be true. The K tells me what happens. I mean, what distribution do I get or what do I do next, depending on whether it was true or false. So if the coin flips true, I do K true. If the coin was false, I do K false. Now I recursively use prop pure to convert those two into probability distributions, maps from A to rational. So now I have two probability distributions, one for true, one for false. So what is now the overall outcome of my experiment? Well, I must now add the two distributions, but I must weigh them accordingly, according to probability P. So I multiply the first distribution with P, the second one with 1 minus P, and then I add them. And that's exactly right, I think. Okay, and that we can try out. So I had this drop to IO 2 dice, which just like simulates it in IO. I can of course do that like 1,000 times and see, but now I have the second interpreter, prop pure, which just gives me the precise probabilities immediately as a map. So we have 7 happens with probability 1 over 6 and 2, for example, only with probability 2, 1 over 36. And of course I could, I mean, I was so proud of my Monty Hall example, and we could now more or less literally copy the code. I mean, this actually we can, I mean, it's so short that we can even do this. I think, though we only have 2 minutes left or something.
5 minutes.
Oh, 5 minutes. So the only thing I have to change is, so now I don't have this monad prop anymore. Instead, I have my prop free monad. Okay, and I have this non-empty, so I must import. That's the only thing missing. Import data.list.non-empty qualified SNE. See, now the old code or pick is, oh yeah, but that I mean, luckily I can also just take that and use it. That was this, how I can pick a random element from a non-empty list. So that I can also just copy over here. And all I have to do is change the signature. And of course also import non-empty, like unqualified. No. Okay. Let's check. So the pick, okay, that just compiles as before. So all I had to do was change the signature. And right, my Monty Hall also just compiles. All I had to do was change the signature. And now as before, so, and of course I have now both, I mean, I can do it in IO because I have the IO interpretation, prop to IO, let's say replicate, sorry?
You need to reload large scripts.
Yeah, probably. Thank you. And that. So I could do like prop to IO, replicate M 100 times, Monty Hall, okay, stay the stupid strategy. And I should see that there are lots more falses than trues. And if I do the smart strategy, there are much more trues than false, but it's still, of course, not obvious. And now I can also use my prop pure. And I see, okay, if I use the stupid strategy, I lose with 67% probability and I win only with 33%. And if I use the smart strategy, I win with 67% probability and lose with 33%. So in just like that. But I mean, yeah. I mean, it's very similar. So, I mean, what I did back then, this type class approach that I said, okay, I define a class monad prop for a monad M, which has this additional functionality. And then I wrote the two instances, one for IO and one for this list, pairs of outcomes with probabilities. And then I could write my programs. And here it's very similar approach. I mean, the code, a lot of the code is almost literally the same. However, I mean, here, for example, in order for this to make this distant instance, I had to work quite hard. I mean, I had to implement bind and pure and so on by hand. And then I had to do like this map stuff. And now this is basically a one-liner. I mean, the prop pure is very short now, and I don't have to do this intermediate step that I first need this dist monad. So yeah, in that sense, this is actually better.
Yeah, so cool.
Okay, yeah, time is basically up. Are there any last questions?
I don't know. Guys, you have any questions?
Okay.
I think no
Yeah,
questions so far. Yeah.
okay. I mean, I really like free monads. I think it's nice because you can first think just about the operations you need and basically see whether I mean you have everything you need to write your program, whatever it is, and then with these different interpreters. I mean, here in this example, I think it's a nice example with that you just need. I mean, to do probability stuff, all you need is basically this operation that you can flip. I mean, this operation actually. So you want a monad where you can do a coin flip with a given probability. Or I mean, also this previous example with the poor man's concurrency is also very nice, I think. I think all you need is like atomically, I mean, yeah, do like IO stuff in one thread atomically, which can't be interrupted, and then fork other threads. Or as I said before, I mean, you could enhance that and do like an operation to open a channel, and then an operation to send on a channel, and to wait on a channel, and then that then gives you inter-thread communication, and you can do all these things and basically just think about the operations you need without worrying how to actually implement it. So I think it's a nice perspective on certain types of things. Yeah, you don't really need to do it. I mean, there's always this type class approach as well. But yeah, I like free monads. I think they're very, very neat. And it's, as I said, the second way now to, I mean, so basically it's very rare that one needs to write a monad instance by hand. And of course, the nice thing is that both, I mean, MPL and also free monads, they basically guarantee that the monad laws hold. So you don't have to worry about that either. So as long as you start with a functor, I mean, the free monad will be a law-abiding monad. Same for MTL. If you start with some base monad, then, I mean, at least I mean, I mentioned last time there is a problem with list T that is actually broken. So it doesn't give you law-abiding monad, but the others like state T, reader T, accept T, they're good. So yeah, so in practice, nobody really ever, except some researchers maybe, implements a monad by hand. So it's normally you always use MTL or these effect systems that also exist, or free monads, or a combination of that. There's actually also a free monad transformer. So maybe that's the last thing I say for today. If we look at this, I mean, this control monad package, or sorry, the free package. There's also a control monad trans free, and then you have a free T transformer. So that actually, given a base monad and a functor f, it basically freely adds these operations to an arbitrary monad. So you can start with an existing monad, and then again, like our free is basically free TF identity. I'm not sure how often that is useful, but it's also quite cool. So you can already start with something like state or whatever, and then add arbitrary operations on top of it. And then, of course, if you want to actually do something with them, you still need an interpreter. But nevertheless, that's also quite cool. So there's also that free monad transformers. Okay. But
Yeah. Samson's comment say, love the monthly hold example.
yeah, I love that too. Very pleased with that. Okay, then thank you very much, and talk to you on Thursday, I think.
Yeah.
Okay.
Thank you.
Thank you. Bye. Bye.
Bye.
Bye.